So in the previous lecture, we discussed about Langevin's classical theory of diamagnetism. Today we'll be discussing about the Langevin's classical theory for paramagnetism. Before we dive into this topic, we'll discuss what paramagnets are. We'll just understand what paramagnets are. So paramagnets is like the opposite to diamagnet in certain senses. So in case we'll just compare and study. So paramagnets and diamagnets, the susceptibility for diamagnets was negative. So it was negative susceptibility. It was due to the Lenz's law, whereas in case of paramagnets is positive. In case of diamagnets, there were no unpaired electrons. So unpaired electrons was not present. Whereas in case of paramagnets, the unpaired electrons are present. Sorry, they were not present and they're present. Okay. Here, in case of paramagnet, the dipoles are non-interacting with or without the external magnetic field, and individual magnetic moments of an atoms or molecule experiences a torque. They align with the magnetic field, but alignment is incomplete due to interaction with nearby atoms and thermal agitation. That means so let's talk about absence of magnetic field first and then jump into the presence of magnetic field. So in the absence of magnetic field, the net magnetic moment, atomic magnetic moment is 0 because they have unpaired electrons. Whereas in case of presence of magnetic field, they will align. They'll align. The alignment of dipole will happen, and the net magnetic moment will be m is equal to susceptibility chi m h. Okay. So in case of paramagnetic material, each individual atom possesses a permanent magnetic moment, but due to thermal agitation, there is no average moment per atom, and therefore m is equal to 0. In the presence of applied magnetic field, the individual magnetic moment takes alignment along the applied field, and m is infinite along B. So that's that. So there's this threshold temperature called the Curie temperature. If it is above the Curie temperature, then it's paramagnet, and if it's below the Curie temperature, paramagnets, and if it's below the Curie temperature, it will be ferri or ferromagnets. Okay, ferri and ferromagnets above the Curie temperature, and then below that is paramagnets. Fine, I hope you understood what paramagnet is. So if temperature increases, the magnetic field decreases. So at low temperature and high magnetic field, we write susceptibility equal to m by h, where m is equal to n nu b by h. Okay. So here, nu b cos theta is nothing but the component of the magnetic moment with respect to the applied field, and we are assuming this gas as a molecular gas so that we can take we can use Maxwell-Boltzmann distribution here. Therefore, dN is equal to e raised to minus e by kt dE, where dN is a smaller number of particles which are oriented in the direction theta, with which the energy goes from E to E plus dE. E as potential energy, where that is E is equal to minus nu m b, which is equal to minus nu m b cos theta. Cos theta. Okay. dE is nu m b sin theta d theta. Okay. Now you substitute this value into dN. You'll get the formula dN is equal to e raised to minus minus become plus minus mu m b cos theta divided by kt into nu m, one second, nu m b sin theta d theta. Okay, here nu mb by kt, this term without the cos term, is assumed to be alpha and nu mb is assumed to be c. So rewriting the equation, we'll get it like this: dn is equal to c e raised to alpha cos theta sin theta d theta. Okay, so we know in dn we need n is nothing but the integral of it. We'll get it as c e raised to this is c, okay, c e raised to alpha cos theta sin theta d theta, and from this we can find m. So m is nothing but from m we'll find susceptibility. Ultimate goal is to find susceptibility, but we'll go step by step. So m is equal to nu m n nu m, so nu m cos theta into integral dn, n, we can say n, but integral dn 0 to pi. You can directly write it as n also, no problem. Maybe, okay, I'll write it as n itself, maybe we'll get confused. So you just have to substitute it. You'll get integral c e raised to alpha cos theta sin theta d theta. Now you substitute t to be equal to cos theta, dt is equal to sin theta minus sin theta d theta. Substitute those values, will get it as minus c nu m outside the integral e raised to alpha t dt, and there's a t, okay, t dt. Now you just have to, so now you got the value of m. Okay, now you have to find m in terms of saturation, magnetization and Langevin field. That is, m is equal to ms saturation magnetic field and Langevin function. So in the statistical mechanics we have done this derivation to find the Langevin function, and it turned out to be cot h alpha minus 1 by alpha, where cot h alpha was 1 by x plus x by 3 minus 2x cubed by 45. This derivation was done in the statistical mechanics course. And the saturation magnetic field, m is nothing but saturation magnetization is nothing but nu m. You just have to substitute it here, the value, so it will become n nu m cot h alpha minus 1 by alpha. Substitute the value n nu m cot h alpha 1 by x plus x by 3, oh sorry, not x, alpha. Here the x is alpha, so 1 by alpha plus alpha by 3, and then we use for the first two terms, that's fine. And then this is alpha, okay, I thought that was 2 for a minute. Okay, that's not 2, that's alpha minus 1 by alpha. So the equation reduces to alpha by 3. So you just have to write n nu m into alpha by 3. Okay, that is m. Fine. Now from here we know what alpha is, right? Alpha is something but nu mb by kt. You just have to substitute it there. You will get it as n nu m divided into nu mb by kt kbt into 3. There's a 3 here. Oh, that's the correct answer. The way I wrote was correct. Yeah, nu mb by kt. Yeah, where mb is equal to, yeah, sorry, not 0. So Yeah, you just okay. So you got the equation for m. Now you can find susceptibility from here. Susceptibility is psi is equal to m by h. Substituting the value of b here, you will get n nu square m. B is nu 0 h divided by 3 kbt into h. These h cancels. You will get n nu square nu naught divided by 3 kbt. So susceptibility, from this equation we can see that susceptibility psi is inversely proportional to temperature. And then the proportionality constant is nothing but c by t, where c is this whole term except the t term. This is c, where c is the Curie constant. Okay. So this is how the graph looks like. Susceptibility versus temperature, it will be decreased, decaying process. Okay. So let's recap. So we were talking about paramagnetism. So paramagnets means they have unpaired electrons, and their susceptibility is positive. And if it's if the temperature is above the Curie temperature, then they are paramagnet. If it's below that, then it's ferromagnet to ferrimagnet. We started with susceptibility. Susceptibility is nothing but m by h. Here, okay, m by h, m is equal to nub by h. Here we consider it as an molecular gas, so we can use Maxwell-Boltzmann distribution, where dn is equal to e raised to minus e by kt de, and e is nothing but nu 0 m b dot b, and you just have to substitute it. You will get the equation for n. And then you have to substitute it back here. You will, for m is equal to nub, you get it like this, in this form. So here you know that we substitute few values. We take alpha to be nu 0 m by kt and c to be equal to nu 0 m. From here we want to find this thing m in terms of ms and Langevin function. And Langevin function we studied in the statistical mechanics, that it's cot h alpha minus 1 by alpha. We know cot h is nothing but 1 by alpha plus x by 1 by alpha plus x alpha by 3. You just have to substitute. Finally you get it as this form, and alpha we found it earlier to be nu b by kt, nu mb by kt, and you just substitute it here, and then you find susceptibility n nu square m. B is nothing but nu 0 h, and then divided by h. You will get it like this. And finally you can see that susceptibility is nothing but inversely proportional to T, and this term, the rest of the term, is C, where C is a Curie temperature. I hope you understood this much. That's all for today's video.